Hello. Thanks, Eves. I'm Andrew Howard from the National Computational Infrastructure located at the ANU in Canberra, Australia. I'll be talking to you today about expanding clouds using high-performance InfiniBand interconnects. Firstly, I'd like to thank my colleagues who did all the hard work on this project. Jacob Krajicek, our NCI Cloud Team architect, Dr. Kenneth Ban from A-Star, and Mr. Jonathan Lowe, also from A-Star. NCI is Australia's national computational infrastructure. We deal in high performance, computing, clouds, storage, overlaid on networks. I'll be talking to you today about one of our projects called InfiniCloud. We run a number of virtualization and cloud services, starting with VirtualBox for service development, and using Openstack for our Nectar, ROS, Tengen, and InfiniCloud platforms. We also have a development and testing cloud. We use a number of VMware production and internal services, and we are exploring Docker for a lower cost virtualization option. I'd like to talk to you today about NCI InfiniCloud. We were posed a number of questions. Can we use Openstack to create mini high-performance computing instances with InfiniBand to support workflows which perform better with local solid-state disk storage? Can we use this as a provisioning system for bare metal only, or can we also run virtual machines? And what performance penalties do we pay for running InfiniBand within a virtual machine context? Our challenges were to provide the high-performance computing capabilities based on InfiniBand of RDMA, MPI, IP over IB, combined with a Lustre file system, with the convenience of clouds, the rapid deployment, NSF and Ceph, solid-state disk storage in a secure manner with high-speed data access. The model we came up with was InfiniCloud, which is an OpenStack-based cloud running virtual machines connected to an InfiniBand fabric and supporting Lustre file system access. While we were designing this platform, we were challenged with Supercomputing 14 held in New Orleans, and were asked, can we make this work at intercontinental distances and demonstrate at Supercomputing 14? In collaboration with A-Star, NCI and A-Star collectively decided to utilize a trans-Pacific extended InfiniBand and shared supercomputer resources to accelerate genetic DNA analysis. These are large, around 300 gig genetic sequence transfers generated in Canberra and transferred from NCI to A-Star in Singapore for analysis on A-Star's large memory Aurora system. We also utilise NCI's high-performance InfiniBand Cloud HPC system InfiniCloud for visualisation of genetic datasets and the results produced by the Singapore Aurora system. This diagram shows our genetic sequence workflow. Originating from an Illumina HiSeq 2500 device at the John Curtin School of Medical Research, we generate a 381 gig dataset, which is then transferred to Singapore, processed using BWA on Aurora, and the resultant 1.14 terabyte dataset returned to NCI in Canberra. To achieve this, we built a trans-Pacific light path. Australia is connected to Asia via two paths, a smaller western path with 2.5 gigabit capacity, and a more capable eastern path with multiple 10 gig capacity. We tested our data transfer scenarios on both networks, but for the sake of a production network and having 10 gig, we chose the Pacific path, which results in a 30,000 kilometre cable length with around a 305 millisecond delay time. Integral to this operation was equipment supplied by an organisation called Obsidian Strategics, who have kindly loaned us both their crossbow InfiniBand switch and a number of longbow E-series InfiniBand extenders. Our extended InfiniBand fabric was based in Singapore with a star topology connecting partners in Japan, Australia, 2 sites in the US, one at the show floor at Supercomputing, the other at Georgia Tech. We ran 2 experiments. The first, an Australian to Singapore large data transfer, where processing occurred in Singapore on the Aurora system, and the data was returned to Australia. Our second experiment was a Singapore to Australia data transfer, where we processed on InfiniCloud and we viewed the results at Supercomputing 14. Significant were the data transfer speeds that we achieved using InfiniBand over traditional TCP/IP networks. On a 1 gig circuit, a traditional rsync transfer takes 4 hours and 7 minutes to complete. Using Obsidian's proprietary desync utility operating over an InfiniBand fabric, we were able to reduce this time to 1 hour and 21 minutes. The same transfer over a 10 gig circuit took 3 hours using traditional TCP tools and was reduced significantly to 7 minutes using Obsidian desync and our extended InfiniBand fabric. A 1.14 terabyte dataset using traditional TCP tools over a 1 gigabit network requires 12 hours 33 minutes to transfer. Using Obsidian, this time was reduced to 4 hours and 5 minutes in the 1 gig case, and the traditional 9-hour rsync transfer over a 10 gig TCP network was reduced to only 24 minutes. Our observed data rate between Singapore and Australia was consistently around 900 megabytes per second, indicating a link utilisation of almost 100%. These numbers have been extrapolated out to give you some idea of data transfer capability over some normalised time periods. Also significant is the small delta of around 10 to 15% in performance we achieved by operating in a virtual machine context. Our bare metal 900 megabyte per second transfers operated in the range of 750 to 800 megabytes per second. I should note that this is not a dev zero to dev null copy operation as normal benchmarks portray. All tests used actual data from an Illumina 2500 genetic sequencer or an uncompressed high definition 1920 by 1080 video file to replicate actual and not synthetic workflows. Solid-state disks were attached to each node for data storage. These are our suggested desync parameter settings for a long delay 305 millisecond connection between Singapore and Australia. So, we've achieved high performance InfiniBand within a cloud, and it's called InfiniCloud. This is an Openstack supported cloud running a 56 gigabit per second FDR InfiniBand fabric. We have high performance InfiniBand MPI, high performance Lustre file system access. It's built using Mellanox Neutron modules, provides flexible top performance computational resources on demand, and has HPC quality with images curated and managed by our application stack team and supported by an I/O architecture which includes local solid-state disk and high-performance large file storage connected to our main Lustre file stores. We achieved this during the Nova to Neuron transition. Nova networks were replaced by many private neutron networks and allowing public networks to connect tenants to the internet. Most significantly, this provides us with a flexible SDN network setup which we can use to engineer InfiniCloud. Neutron supports many plugins, including the Mellanox and Neutron agents. The Mellanox plugins provide support for both 56 gig Ethernet and native InfiniBand operation. However, it should be noted that specific hardware and version requirements of firmware in systems and cards add complexity for provisioning. The Mellanox FDR InfiniBand provides us native InfiniBand installation of Openstack, which requires some degree of modification to core components in the same way as 56 gigabit Ethernet does, with the addition of replacing the default DHCP with a custom DHCP which supports InfiniBand, using the OpenSM configuration mapping of PKIs and Ethernet VLANs, and the Neutron hypervisor and Nova Compute also needed to be configured. Details on some of the configuration can be found here. External communication is exclusively Ethernet. OpenSM is required to maintain Fabric, and we are migrating to BGFC with a feature request submitted for operation in virtual mode. The results of InfiniBand as a component of a global InfiniCortex are that VMs hosted at NCI in Australia can communicate over RDMA with both physical machines and VMs hosted at A-Star in Singapore. The Obsidian desync data transfers yield approximately 800 megabytes per second within a VM. This is part of an ongoing collaboration between NCI, A-Star and NUS in Singapore, and we are now processing 1 terabyte plus genomic data sets with Elastic Cluster. However, this has not come without some interesting challenges. OpenSM stability in these distances is pushing the product far beyond its intended design. We're seeing great data transfer numbers with Obsidian desync. So we asked ourselves, how can we utilize this technology for other large data transfers? We also needed to perform some IP over IB tuning. We are starting to understand the components which we need to do further work on. And we've observed around 10 to 15% performance cost for virtualization of InfiniBand for large data transfers. Further testing and characterization of MPI performance and inter-VM performance has been completed by the A-Star team and published at the Supercomputing Frontiers 2015 conference this week. So our next question was, can we open this up to an actual bioinformatician who understands the limitations of the system but is prepared to experiment? Dr. Kenneth Ban from A-Star in Singapore was kindly able to assist us in this task. And together we have created a Bioinformatician operating at NCI and A-Star in Singapore, which is capable of sequencing genetic data from Illumina 2500 and Illumina X10 systems. The Bioinformatician workflow includes provisioning of using Elastic Cluster, a data ingest phase, processing with BWA, and then data export. The Elastic Cluster system provides dynamic provisioning of NFS servers for data access. We operate a 1-to-1 core to VM CPU ratio. We're using CentOS 6.6 as the guest operating system. And we've used the module package manager for compatibility with our HPC systems. And of course, desync is used for data movement between Australia and Singapore. Australia has a number of big data challenges. On the astronomy side, our existing radio and optical facilities, the SkyMapper telescope, and currently the SKA Pathfinder, and as we move forward, the full implementation of the square kilometre array. We also have geographically shared data on climate, environment, biology and health, particularly in the area of plant phenomics and genetic sequencing. Genetic sequencing forms the next large data explosion. Currently, many organisations use the Illumina HiSeq 2500 system. These are currently being replaced by their newer generation model, the HiSeq X10. Each X10 is capable of producing the same workflow as 25 Illumina 2500s. It should be remembered that the cost of genetic sequencing has fallen since its inception of around $1 billion and 10 years to achieve a sequence, to something in the order of $1,000 and 3 days currently. So what benefit can this provide? Personalised medicine and pharmaceuticals, which are a significant cost reduction in genome mapping, moves this into the pricing realm of other standard clinical diagnostic tests. This allows for better drug selection and better patient outcomes. I'd like to point you to a number of reference papers. InfiniCortex describes a concurrent supercomputing across the globe utilising transcontinental InfiniBand and a galaxy of supercomputers. Also, we've performed some performance assessments of InfiniBand high-performance computing cloud instances on Intel Haswell and Intel Sandy Bridge, and written a paper on InfiniCloud called Leveraging the Global InfiniCortex Fabric and Openstack Cloud for Borderless High-Performance Computing of Genomic Data and Beyond. So where to now? We're on the path to exascale computing. This leads to lots of interesting questions for our community to research and answer. How can we optimally support our legacy TCP workloads in this environment? Can InfiniBand scale globally? Can we accelerate classes of science problems? And what are the performance characteristics of HPC systems with a high-speed interconnect but a predictable transcontinental latency? What are the optimal routing topologies? Can they be virtualized on a workflow basis for optimized communication? And how can we manage authentication, authorization, and collaboration in a multinational environment? This is only one of many of our successful user stories of pioneering science built on the foundation of evolving and powerful high-performance networks and supercomputers. It only takes someone with an interest in trying something new, building the trust, and achieving something astounding to change the world. That concludes my presentation, but I'd like to thank our collaborators at A*STAR, the ANU John Curtin School of Medical Research, the kind support of Obsidian Strategics, our partners at SingerN, ARNet, Pacific Northwest Gigapop, and ESNet, and of course, anyone else we've forgotten to thank. Thank you very much.